In this video, we introduce a new class of functions which are called the hyperbolic functions. There are two basic hyperbolic functions, and these are defined in terms of the exponential function. So the first of the two basic hyperbolic functions is cosh x, which is e to the x plus e to the minus x divided by 2. Now, we know what the graph of e to the x looks like. We know what the graph of e to the minus x looks like. So what does the graph of y equals cosh x look like? So, there's my diagram showing the graph of e to the x and also the graph of e to the minus x. For cosh x then, well, first of all, let's have a think about what happens when x is 0. If we've got x equals 0, e to the nothing is 1, so cosh of nothing is going to be 1 plus 1 divided by 2, so that gives me 1. If x is a large positive value, then e to the x is very large and positive, e to the minus x is small and positive, so it's very close to 0. So, for a large positive value of x, cosh x is going to be roughly the same as a half of e to the x. Of course, e to the minus x is insignificant. If we've got a large negative value of x, on the other hand, the value of e to the x is very, very small, very close to 0, whereas the value of e to the minus x is going to be very large and positive. So if x is a large negative value, then the cosh x is very, very close to just being a half e to the minus x. Put these two pieces of information together, then we ought to be able to see that the graph of y equals cosh x is going to be a U-shaped type graph, looking like that, with it looking like e to the x, or half e to the x rather, for large positive values of x, and it looks like a half e to the minus x for large negative values of x. The second of the major exponential functions is sin x, which is e to the x minus e to the minus x divided by 2. Now again, you can think about the graph of y equals sin x by starting off thinking about the graphs of e to the minus x and e to the x. Now just take a moment or two to have a think about these two graphs and try and sketch on a piece of paper what you think the graph of y equals sin x will look like. When x is nothing, sin x is going to be 1 take away 1 divided by 2. In other words, sin x is going to be 0. If x is a large positive value, then e to the minus x is going to be pretty well insignificant. It's very close to 0. So sin x is going to be very close to a half e to the x. On the other hand, if x is a large negative number, then the value of e to the x is very close to 0. So the value of sin x is going to be very close to minus a half e to the minus x. And altogether, that leads us to a graph looking something like that for y equals sin x. So we've got the two basic hyperbolic functions. Cosh x is e to the x plus e to the minus x, all divided by 2. Sin x is e to the x minus e to the minus x, divided by 2. You'll notice that the names of these two hyperbolic functions are very, very similar to the names of trigonometric functions. And the reason for that choice of name is that they have properties that are very reminiscent of trigonometric functions. So consider, for example, cosh squared x minus sin squared x. Well, if we make use of the definitions, cosh x is e to the x plus e to the minus x over 2. So cosh squared x is e to the x plus e to the minus x over 2 all squared. And then sin squared x is going to be e to the x minus e to the minus x all over 2 squared. So multiplying out the brackets, we've got cosh squared x is e to the x squared plus 2 lots of e to the x times e to the minus x plus e to the minus x squared, all divided by 4. And then we are subtracting sin squared x, and the expanded form for sin squared x is going to be e to the x all squared, take away 2 e to the x, e to the minus x, add e to the minus x squared, all divided by 4. Now, if we try and simplify that, e to the x squared is e to the 2x, e to the minus x squared is e to the minus 2x, and e to the x times e to the minus x is just 1. So the expression for cosh squared x simplifies itself down to e to the 2x plus 2 plus e to the minus 2x, all divided by 4. Similarly, the expression for sin squared x simplifies itself down to e to the 2x minus 2 plus e to the minus 2x, all divided by 4. And this simply simplifies down to 2 over 4 minus 2 over 4, which of course just makes 1. So we have proved that cosh squared x minus sin squared x is always equal to 1. Let's have a look at another example. Let's have a look at sin a cosh b plus cosh a sin b. So, writing out the definitions of that, we've got e to the a minus e to the minus a all over 2 times by e to the b plus e to the minus b over 2 plus e to the a plus e to the minus a over 2 times by e to the b minus e to the minus b over 2. If we expand the two brackets that we've got, the first double bracket expands out to give me e to the a times e to the b plus e to the a e to the minus b minus e to the minus a e to the b minus e to the minus a e to the minus b all over 4. Whilst the second double bracket expands out to give me e to the a e to the b minus e to the a e to the minus b plus e to the minus a e to the b minus e to the minus a e to the minus b all over 4. And if we simplify that, we notice that several of the terms cancel out. And we are simply left with e to the a plus b, take away e to the minus a plus b, twice over. So that gives me e to the a plus b minus e to the minus a plus b over 2. Now we know that e to the x minus e to the minus x divided by 2 is equal to sin x. So e to the a plus b minus e to the minus a plus b over 2 is just going to be sine of a plus b. So we've got sine a cosh b plus cosh a sine b is equal to sine of a plus b. Okay, now what I'd like you just to do at this stage is to pause the video and use a similar method to the previous example to prove that cosh a cosh b plus sine a sine b is always going to be the same thing as cosh of a plus b. So pause the video and just work through that question. Okay, I hope you found that reasonably straightforward. So we've now established three results. We know that cosh squared x minus sine squared x is always equal to 1, that sine a cosh b plus cosh a sine b is sine of a plus b, that cosh a cosh b plus sine a sine b is the same thing as cosh of a plus b. Now, we just need to make one or two little observations. First of all, cosh of minus x is the same thing as e to the minus x plus e to the minus minus x divided by 2, which is the same thing as e to the minus x plus e to the x over 2, which of course is the same thing as e to the x plus e to the minus x over 2, which is cosh x. And similarly, we can see that sine of minus x is the same thing as minus sine x. Now, making use of those results, we can deduce that sine of a minus b is the same thing as sine of a plus minus b. Now we know that sine of a plus another angle is going to be sine of a cosh the other angle plus cosh of a sine the other angle. So sine of a plus minus b is going to be sine a cosh minus b plus cosh a sine minus b. Cosh of minus b is the same thing as cosh b. Sine of minus b is the same thing as minus sine b. So we're ending up that sine of a minus b is sine a cosh b minus cosh a sine b. Similarly, cosh of a minus b is the same thing as cosh of a plus minus b. So that's cosh of a cosh of minus b plus sine of a sine of minus b. We know that cosh of minus b is the same thing as cosh b. We know that sine of minus b is the same thing as minus sine b. So we're ending up with cosh of a minus b is cosh a cosh b minus sine a sine b. Okay. If we put a and b to be the same, then we obtain sine 2a is the same thing as sine of a plus a, that's sine a cosh a plus cosh a sine a, that's 2 lots of sine a cosh a. Cosh of 2a is the same thing as cosh of a plus a, so that's going to be cosh a plus sine a sine a. In other words, it's going to be cosh squared a plus sine squared a. Now we're going to look at solving equations involving hyperbolic functions. And there's going to be two approaches that we can use. We can either return to the basic definitions of the hyperbolic functions, or on some examples we can use the identities that we've just established. So let's have a look at the first example. Solve the equation 4 cosh x plus sine x equals 12. Well, we can rewrite that straight away as in terms of e to the x's. We've got 4 lots of e to the x plus e to the minus x over 2, which is cosh x, plus e to the x minus e to the minus x over 2, which is sin x, must equal 12. If we tidy that up, we can first of all multiply by 2 to clear the fractions out. We've got 4 lots of e to the x plus e to the minus x, plus e to the x minus e to the minus x must equal 24, which tidies up to 5 e to the x plus 3 e to the minus x equals 24. Remember that e to the minus x means the same thing as 1 over e to the x. And then it's clear that what we need to do is just multiply up by e to the x. If I multiply up by e to the x, I get 5 lots of e to the x squared plus 3 equals 24 e to the x. In other words, I've got a quadratic equation in e to the x. So rearranging, we've got 5 e to the x squared minus 24 e to the x, add 3 must equal 0. Solving the quadratic equation tells me that e to the x is either 4.67 or 0.128. So we can now simply take logarithms and obtain the fact that x must be the logarithm of 4.67 or the logarithm of 0.128. In other words, x is either 1.541 or minus 2.052. The second example, we want to try and find the exact solutions of the equation sin squared x plus 7 cosh x equals 17. And at this stage, the thing to do is to remember that we know that cosh squared x minus sin squared x is always equal to 1. So rewriting that, we can say that sin squared x is equal to cosh squared x, take away 1. And we can then eliminate the sin x and get the whole equation in terms of cosh x. So we've got sin squared x plus 7 cosh x equals 17. Tells me that I've got cosh squared x minus 1 add 7 cosh x equals 17. In other words, we've got cosh squared x plus 7 cosh x minus 18 must equal 0. So what I've got now is a quadratic equation in cosh x. So solving that quadratic equation, we've got cosh x plus 9 times by cosh x minus 2 equals 0. In other words, cosh x is minus 9 or cosh x is 2. However, if you go back and think about the graph of cosh x, or the definition of cosh x, we know that cosh x is always positive. So we can forget the cosh x equals minus 9 possibility. So we've simply got cosh x equals 2. Now I want exact solutions for this, so we've got e to the x plus e to the minus x divided by 2 equals 2. So that's e to the x plus e to the minus x must equal 4. If we times through by e to the x, that gives me e to the x squared, add 1 equals 4 e to the x. So we've got the quadratic equation in e to the x now. So I've got e to the x squared minus 4 e to the x, add 1 equals 0. Solving that quadratic equation for e to the x will give me e to the x is either 2 plus root 3 or 2 minus root 3. And that tells me that x is either the logarithm of 2 plus root 3 or it's the natural logarithm of 2 minus root 3. And in this case, since the question said find the exact solutions of the equation, we'll leave our answer just like that. For our next equation, we're going to try and solve sine squared x plus 5 cos 2x equals 104. If we had been trying to solve a similar trigonometric equation, for instance, sine squared x plus 5 cos 2x equals 3, then the approach would have been to rewrite the cos 2x in terms of sine x using the trigonometric identities. And we're going to do a similar thing here. We're going to try and rewrite the cos 2x part of the expression in terms of sine x. So, we know that cos squared x minus sine squared x is always equal to 1. We know that cos squared x plus sine squared x is always equal to cos 2x. If I take equation 2 and subtract equation 1, I get cos 2x minus 1 is 2 sine squared x. In other words, I know that cos 2x is the same thing as 1 plus 2 sine squared x. Substituting this into the equation that we've got now gives me sine squared x plus 5 lots of 1 plus sine squared x must equal 104. In other words, we've got 11 sine squared x plus 5 must equal 104. Or sine squared x equals 9, which in turn gives me that sine x must equal 3 or minus 3. If we've got sine x equals 3, that now gives me the equation e to the x minus e to the minus x over 2 equals 3. Multiplying up by 2 gives e to the x minus e to the minus x equals 6. Multiply through by e to the x, now gives me e to the x squared, take away 1 equals 6e to the x. So I've now got my quadratic equation in e to the x, which I can solve as e to the x is either 3 plus root 10 or 3 minus root 10. 3 minus root 10 is a negative number, so we can throw that one away. E to the x cannot possibly be a negative number. So we've got e to the x is 3 plus root 10, which gives me x equals the natural logarithm of 3 plus root 10. On the other hand, if we've got sine x equals minus 3, very similar working will lead me through to the equation e to the x squared plus 6e to the x minus 1 equals 0, and that in turn leads me down to x being the natural logarithm of minus 3 plus root 10. Now, we've introduced the first 2 hyperbolic functions. There are in fact 4 more hyperbolic functions that we need to introduce. The first one of which is tanh x, which is sine x over cos x, which we could of course write as being a half of e to the x minus e to the minus x over a half e to the x plus e to the minus x. The halves cancel, so tanh x is the same thing as e to the x minus e to the minus x over e to the x plus e to the minus x. The first thing that should be obvious is that tanh 0 is 0 because sine 0 is 0 and cos 0 is 1. If we look at the expression tanh x equals e to the x minus e to the minus x over e to the x plus e to the minus x, and multiply the top and the bottom by e to the minus x, then we obtain an alternative expression for tanh x, which is that tanh x is e to the x times e to the minus x minus e to the minus x times e to the minus x over e to the x times e to the minus x plus e to the minus x times e to the minus x. In other words, that tanh x is 1 minus e to the minus 2x over 1 plus e to the minus 2x. Now, as x tends to infinity, we know that e to the minus 2x tends to 0, so this tells us that as x tends to infinity, tanh x tends to 1. Similarly, if we go back to the e to the x minus e to the minus x over e to the x plus e to the minus x expression, and multiply the top and bottom by e to the x, then we obtain tanh x equals e to the 2x minus 1 over e to the 2x plus 1. As x tends to minus infinity, e to the 2x tends to 0, so tanh x is going to tend to minus 1. So we know that tanh of 0 is 0. As x tends to infinity, tanh x tends to 1. As x tends to minus infinity, tanh x tends to minus 1. So we've got our graph of tanh x. The second of our new hyperbolic functions is going to be, and this one I always found very difficult to pronounce, sec x, being 1 over cos x, which we can write as being 1 over a half of e to the x plus e to the minus x, or 2 over e to the x plus e to the minus x. Now, as x tends to infinity, we know that e to the x tends to infinity, e to the minus x tends to 0, so we've got 2 over a very large number, so we can see that sec x is tending to 0. Similarly, as x tends to minus infinity, e to the x tends to 0, e to the minus x tends to infinity, so sec x is tending towards 2 over a very large positive number. In other words, sec x is tending to 0. We know that cosh of 0 is 1, so sec of 0 is also going to equal 1. So our graph of y equals sec x looks something like that. The third of our new hyperbolic functions is cosec x, which is just 1 over sin x. Now, we know that sin 0 equals 0, so the graph of y equals cosec x is going to have x equals 0 as an asymptote. As x tends to plus or minus infinity, sin x tends to plus or minus infinity, so the graph of y equals cosec x is going to have y equals 0 as an asymptote as well. So we're ending up with a graph looking something like that. And finally, cos x is 1 over tanh x. We know that tanh of 0 is 0, so the graph of y equals tanh x is going to have x equals 0 as an asymptote. We know that as x tends to plus or minus infinity, then tanh x tends to plus or minus 1, respectively. So that means that the graph of 1 over tanh x is also going to have y equals plus or minus 1 as asymptotes. So our graph of y equals cos x is going to look like this. Now, many of the properties of these new hyperbolic functions are very similar to the properties of the corresponding trigonometric functions. The properties, if we need them, can be proved either using the basic definitions or just calling back on the two key results that are tanh x is sin x over cos x, and cos squared x minus sin squared x is always equal to 1. So let's have a look at solving the equation sec x plus 2 tanh squared x equals 2. Then our first solution, we're simply going to say that sec x is 1 over cos x, and that tanh x is sin x over cos x. So if we multiply through by cos squared x, we've got the equation cos x plus 2 sin squared x equals 2 cos squared x. In other words, we've got cos x is the same thing as 2 cos squared x minus sin squared x, but we know that cos squared x minus sin squared x is equal to 1. So we've got cos x equals 2. Now we've already solved the equation cos x equals 2 in an earlier example, and we saw that cos x equals 2 gives us x equals the natural logarithm of 2 plus root 3, or the natural logarithm of 2 minus root 3. Now there's a second way of tackling this question. So using the second way, we're going to say is, look, we know that cos squared x minus sin squared x is always equal to 1. Dividing through by cos squared x, that gives me 1 minus sin squared x over cos squared x is equal to 1 over cos squared x. In other words, we've got 1 minus tanh squared x equals sec squared x. So solution 2 is going to say that we've got sec x plus 2 tanh squared x is equal to 2. So we know that tanh squared x is the same thing as 1 minus sec squared x. So I've now got sec x plus 2 times 1 minus sec squared x equals 2. So that now gives me sec x minus 2 sec squared x equals 0. In other words, either sec x is 0 or a half, which means that I've got 1 over cos x equals 0 or a half. And that tells me that cos x is 2 or infinity. Well, we can't have an infinite value, so we must just have cos x equals 2. And if we've got cos x equals 2, again, in example 2 earlier on, we saw that cos x equals 2 tells me that x is either the natural logarithm of 2 plus root 3 or the natural logarithm of 2 minus root 3. So in this video we've introduced the 6 new hyperbolic functions, in particular sin x and cos x. We've introduced some of their elementary properties and their graphs, and we've looked at how we can solve equations involving these hyperbolic functions.